on Wednesday. And the next homework is going to be posted on Monday, and it's going to be due in less than a week and a few days. So we need to keep moving because I realize, I look outside and it reminds me winter is here. Okay? So we need to keep moving fast. All right. So what we need to do today, oh, by the way, I forgot, I will send you an email regarding projects because it seems too many students from different departments are communicating with me, and I don't want to have to repeat the same things, okay? So most probably I'm going to write something on the website of the course regarding projects, and then I'm going to ask that you send me an abstract following those guidelines, okay? And the abstract, I may approve it or not. It's up to you to make it relevant to this course. In other words, I'm not interested in a paper presentation on making and destroying bridges and, I don't know, any way too domain specific. I like domain specific things, but the emphasis is in computational statistics. And talking about computational statistics, what we need to do today is we need to finish the discussion on the exponential family. Some of the algebra will look very complicated, but on the other hand, hopefully you will appreciate that the results are so general that you can apply them to many, many problems. And then I have to discuss a little bit, maybe for half an hour, on Bayesian inference for the multivariate Gaussian. And I know one of your homework problems involves similar calculations. Actually, the calculations in one of your homework problems is in the notes. The idea there is that not only you read it and you copy it, you actually repeat all the calculations by hand, okay? In principle, any problem you want in statistics, you can search on the web and find the complete solutions to anything, all right? Because someone has done everything. But we're here to learn, so I trust that you are not going to do this. You're going to be better than that. Okay, let's see. We're going to jump to, let's review a few things from Wednesday. Slide 6. So we defined the exponential family of distributions, which includes many, many distributions. You already have worked on this in your homework set. This is the form. Eta are the natural parameters. We sort of gave a justification that U is really the sufficient statistics, is the function of x basically that defines the parameter theta. This is the only thing you need to know, right? That's what the way we define the sufficient statistics. We had a function g of theta outside, which often we put it inside as using the minus of log of g. That's the function a. We also have written this, g is also 1 over zeta, where zeta is the normalization factor. So we're going to also use this expression today, okay? All right, so just a little bit of a notation, right? So eta are the natural parameters, but let's say eta itself can be a function of another parameter. In some sense, eta maybe it's a function, as we already have proved, a unique function of the moments. And let's call the moments theta. So if in some of the slides you see eta of theta, so eta is, parenthesis theta, you know that eta are the natural parameters, but they depend on some other parameters theta that we may also be interested to compute. All right, so this is the exponential family. Okay. I'm going to go through some of the examples we discussed because I'm going to use some of this, okay? Not the details, but at least in spirit what's on these examples. So we gave, this is a problem from your homework set, to put the Bernoulli distribution in the exponential family. And this is the Bernoulli distribution. You can rearrange it with the exponential, and you can finally rewrite it like this. So this log of mu over 1 minus mu are the natural parameters. G of theta is our function outside. H here is 1. And what is important, and we emphasize, that we immediately can see from here that we can invert this relation and write mu as a function of eta. Okay? So, and it comes out actually that that function is the sigmoid function. Okay? An accident, but that has billions of implications, because this will come handy in ideas of logistic regression and many other problems. Okay? So in your homework set, basically you have to report things that look like that. And if you put a constant factor on one function versus the other, it's not a big deal. It's the same thing, right? We just need to be sure that you recognize this eta times x, or eta transpose x, if x is a vector, and also this function g of eta. And of course a, which is minus log of g. Okay. We discuss about the multinomial distribution, and you really have to write it in m-1 dimensions to make sense. And actually, I'm not going to do any of the other examples today. I'm going to go directly to another homework problem, which I also gave it to you for free. But keep in mind, I don't give everything for free forever. All right? So just once a while. All right, so we did a very fundamental calculation using effectively the normalization of the exponential family. So starting with this equation and differentiating it with respect to eta, you can show directly that the gradient of this function a is the moment of the sufficient statistics. Fantastic result, right? And immediately it tells you, you take a derivative, there is your mean. Okay? So this is going to be very handy. And actually, you know what? You can extend this to higher order derivatives. And let me see where my higher order derivatives are. They have to be on the next slide. So if you take another derivative, you come up that the second derivative of a with respect to eta is actually the covariance of u. And because this is positive definite matrix, we concluded that a has to be a convex function. And if a is a convex function, we concluded that from this relation, mu being, the mean being equal to the gradient of a, that implies that we can invert the relation mu to eta. Obviously, we have shown this in the examples, but you can see there is a unifying proof that this relation from eta to mu is unique. Okay? So we can go from moments to this canonical parameters each way we like, and each way is convenient for our calculations. Okay. So let's jump to slide 27 and do a calculation. I think we did this last Monday. So let's assume that out of the exponential family we have n samples. So what we did is we wrote the likelihood as the product of the likelihood of each of these samples, and we got this nice expression, right? So the product of this function, say, computed at each point n. Then we had the function g of eta. If we multiply this n times, we get g of eta to the power n. And then the exponential becomes eta transpose sum of the u's. Right? Nothing fancy. But what is interesting is, when you do this calculation, immediately you see that this data likelihood also belongs to the exponential family, right? So it's not surprising. We have been surprising